significance test. The question is there a home field advantage? We're going to explore the possibility of having a home field advantage in Major League Baseball. So here's the situation. In 2003, the Major League Baseball season, there were 2,429 regular season games, and it turns out that the home team actually won 1,335 or 24-29, 2000 of the, let me change that. Of the 24-29 games, so of the 2,429 games, which would equivalently be 54.96% of the time. Okay, the question is, could this be deviation from the 50%? Simply be, well, it was natural sampling variation. And, if you would have asked me in the year, in the season for 2005, then I could have gotten closer to 50%, or maybe if we went back to 1993, it might have been 45%. So the question is the variation explainable by natural occurrence, by just sampling variability, or is this a lot of evidence to say that there really does exist some type of home field advantage, at least in professional baseball? We're going to take a significance test one step at a time using Phantom. Okay, P, which is the question, what's the parameter that I'm looking at? Well, what am I actually counting? We have a 54.96%, or we have 1,335 games out of 2,429. What was I counting? Those 1335s were the games that they won at home. So I'm really counting the proportion of home team wins. Okay, the next part. I need to write my null and alternative hypotheses. Well, the null is usually really easy to come by. They kind of almost just pretty much tell it to you in the problem. It's the status quo. It's the absence of any effect. And the effect we're looking at is some home field advantage. So what if it were not really true? How many games would you expect them to win? If it's simply a game of chance and each team is equally matched, then you would expect it to be about 50% of the time. Okay, so that means if I play at home, I would win half of the games that I played at home, and so forth. Now, alternatively, we're looking at its P is greater than 0.5. Now, why would I say that? Because we're talking about a home field advantage, not a home field disadvantage. So we're thinking that if there is an advantage of being at home, then I'm going to win more than 50% of the games. So that's why we get the greater than 0.5. All right, the next part is our assumptions. Now, independence, if we look at just independence for a second, what we're looking at is, on average, one game isn't going to affect the outcome of another game, basically. Okay, now there are exceptions to those rules, but remember, we don't really want to look at the exception to the rule. All right, random. This one's a little tricky for this particular example. This one isn't technically or exactly satisfied because we took the entire season of 2003. Okay, now I'm not interested in just 2003. I'm interested in any game ever played in terms of Major League Baseball. What does make this okay is that if I were to have chosen any season in Major League Baseball, whatever year that would be, then that season should be a representative sample for your professional baseball games. Okay? So in terms of the randomness, this does satisfy what we need it to be. It needs to be a representative sample, okay, of my population. And this is going to give us that representative sample. Okay, the next part, 10%. Okay, 10%. Okay, you have 2,400 and I really can't type tonight. 29 games. which are definitely fewer than 10% of all the games played over the years that baseball has been played. Okay, if there's that many games in 1 year, there's definitely enough games. If we go down just a little bit, we have successor failure here. This one's almost kind of rudimentary. I just need to go through the process. So you multiply 0.5. Remember, this is P0 times N and Q0 times N. In this case, they both happen to be 0.5. Okay, so I multiply those two, and you get 24 or 12, 14.5 for both, which is clearly greater than 10. And those are my assumptions. And notice that I stated each one, and I wrote a sentence describing or did the calculations for each of those things. If the independence and randomness are very much stated in the problem, then you could simply say the problem stated these two and move on. Okay? Just be careful not to address them at all. Okay, let's go down just a little bit. N, we have to name our test. Now, because we have all the conditions that have been satisfied, you have we're allowed to use the normal model, and I'm going to use a one sample Z proportion test, abbreviated in your calculator as a one prop Z test, I believe. Okay, and so what we're going to do next is T. I need to find the test statistic. Well, one of the first things I do, now I am using by hand and showing you the formulas for a lot of this, and I know a lot of it can be done in the calculator, and I have no problem with you working those out in the calculator, but just to kind of go through the process so that you can see it done, I wanted to do it by hand here too. I do use the calculator later on. The standard deviation formula for P hat, okay, is P0 times Q0 over N. Okay, and you divide that, or you work that out, you get 0.01015. It's a pretty small standard deviation. If I bring this down, the next, really what we're looking at is the observed proportion for P hat is 0.5469. I need to know exactly how far away in numbers of standard deviations the observed value is from its hypothesized value. So how far is 0.5469 away from 0.5 in terms of the standard deviation that we just quoted? And that, if you think about it, that's probably going to be pretty far. And it is. Here's my z-score formula for a proportion. We subtract my p hat minus my p0 divided by the standard deviation of my p hat, and I get 4.89, and that's, in terms of z-scores, that's really, really big. Anything beyond 3.5 is really large. Okay, the next step would be simply, now I went ahead and I put the picture in. Anytime that you can draw a picture, fantastic. It's extra points. Not really, but it's always a good thing to show that I really do understand what I'm doing. I can even show you a picture of what this would look like. Okay, so the one sample proportion lies 4.89 standard deviations above the mean, and this is what it would look like. 4 standard deviations above the mean is really far. It's almost 5 standard deviations away from the mean. Okay, if we move on to our p-value, or O, obtaining our p-value, here's what it looks like. In the calculator, we're doing the one prop z test. The inputs, my p0 is 0.5. My x, now they told you x in the initial problem, but if you didn't know x, and they just simply told you a percentage, then I would multiply the p hat that they'd given me by the sample size, and that would tell me what it would be. In this case, they told us it was 1335. Okay, where our sample size was 2429, our output, or p-value, is 0.000005. That's really, really small. Or in other words, extremely rare. Now, rare observations are, well, let's just read it. Okay. The p-value of really, really small number says that the true proportion of home team wins were 0.5. If that were true, then the observed value that we got, which was 54.96%, or any larger percentage, should occur in less than 1 out of 500 million. That's pretty much 0% chance. And so what that means is this, if my null is true, if the true value really is 0.5, then this outcome really shouldn't happen like this. And so if we kind of look down, this is our final conclusion. With a p-value that small, I'm going to reject my null, or reject HO. I conclude that the true proportion of home field or home team wins is not 50%, and you could state there is more than 50% because our alternative was greater than, and that there is strong evidence of a home field advantage. All right, so we went through each of the phantom pieces, Phantom. I put in each part that was important. Okay, using the z-score formula, it's always kind of standard practice to write the z-score formula in and put in the z-score. Even if you do the z-test in the calculator and it gives you the z-score, go ahead and put the formula down and put down the z-score with it, even if you don't actually physically calculate it. All right? This is basically from start to finish. This is how you would take care of a significance test. Go through each of your steps, making sure you address each of the pieces. And the hard part it's going to be is really making the right conclusion and using the right terminology. And this, you can kind of, like with our confidence intervals, you could write a script. This script isn't always the same exact terminology, but it's really close in the way that you state it. You're either going to reject HO or fail to reject O because of a large p-value or small p-value, and you're going to conclude something about the true proportion of the population that you're examining. And you're going to either have strong evidence or no evidence or very little evidence, so things like that. Okay? Keep practicing this. Once you get this down, it will make a lot more sense and it won't seem so abstract.